On March 7, 1944, at 0830 hours, Vice Admiral Jizoburo Ozawa stood on the bridge of the aircraft carrier Taiho, watching the morning sun rise over Linger Road's anchorage off Sumatra. The ship beneath his feet represented 32 months of labor, 16,000 tons of steel, and the entire remaining hope of the Imperial Japanese Navy. Taiho was the only purpose-built fleet carrier Japan had commissioned since the war began. One carrier in 32 months? Ozawa had received intelligence reports 3 days earlier. The Americans had commissioned 17 new fleet carriers in that same period. 17. And they had stopped counting the smaller ones. The numbers made no sense. They violated everything Ozawa understood about industrial capacity, shipyard limitations, and construction timelines. Japan had spent decades building the finest carrier force in the world. The Americans had supposedly started from nothing. Yet somehow, in less a time than it took Japan to build one Taiho, American shipyards were launching new carriers every month. Ozawa knew what those numbers meant. They meant Japan had already lost the war. Yamamoto's warning was not abstract theory. It was a calculation as cold and precise as any naval chart. Every carrier launched, every pilot lost, every ship sunk was a number in a ledger that over time would favor the Americans. Spirit and skill could win battles, but not wars of attrition against a nation that could replace what was lost tenfold, 20-fold, with barely a pause. And so, the war became a race that Japan could not win. Every attack, from Pearl Harbor to the Coral Sea, was a gamble to destroy enough of America's carriers, pilots, fleet before the tide of steel and welders reached critical mass. Japan's victories were brilliant, tactical, almost cinematic, but each one was a temporary reprieve. Behind every sunken American ship, 3 more were being welded, riveted, and painted in shipyards in San Francisco, Norfolk, and Seattle. By mid-1942, the mathematics were becoming impossible to ignore. The Battle of Midway was not just a battle of planes and ships. It was the turning point where numbers, precision, and production collided with skill and courage. For Japanese carriers, experienced crews, and thousands of veteran pilots were gone in a single week. Meanwhile, America's losses, though significant, were rapidly replaceable. Every diagram, blueprint, and assembly line in the United States contributed to a tidal wave Japan could not hope to stop. Ozawa would sit awake, staring at maps and tables, trying to understand how the Americans, so inexperienced, could endure such losses and yet keep coming. The answer was painfully simple and terrifying. They didn't just fight. They built. They counted. They calculated. And every month, every ship launched, every pilot trained, was another step toward a future Japan could never outrun in the end. The carriers, the pilots, the tactics, none of it mattered in isolation. What mattered was the sum of steel, labor, and mathematics. Japan could fight with the fury of the gods, but the Americans were building the inevitability of victory in shipyards thousands of miles away. And that, Yamamoto knew, was a force no courage could match. The decision was brutal, but inevitable. Japan would not rebuild the carriers immediately. Instead, they would stretch their resources, patch together replacements where possible, and hope that tactical brilliance could compensate for the missing fleet. Every shipyard, every skilled worker, every ton of steel would be divided among dozens of competing priorities. Carrier construction would compete with submarines for fuel, with destroyers for steel, with transports for manpower. The arithmetic was unforgiving. Every month spent trying to keep the offensive going cost them time they could never recover. Meanwhile, the Americans were just beginning to mobilize the full scale of their industrial might. Where Japan had 3 yards struggling to meet all demands, the United States had dozens capable of building multiple carriers simultaneously. By 1943, American shipyards were launching Essex-class carriers at a rate Japan could not dream of matching. Each new ship arrived with more aircraft, better design, and crews trained in operational doctrine that, though initially untested, rapidly improved with every engagement. Japan's naval staff, faced with the impossible math, had no choice but to gamble. They would continue to fight with fewer carriers, sending their remaining ships into battles that risked destruction for temporary advantage. They counted on audacity, on speed, on surprise, but each action brought them closer to the limits of what their industrial base could sustain. Every lost ship, every lost pilot, was a debt that could not be paid. The calculation was simple. If the Americans could outbuild them, outrain replacements, and replace losses faster than Japan could, then Japan's victories, however brilliant, were only delaying the inevitable. In Tokyo, the calculations were chilling. The staff looked at the numbers, the shipyards, the months and years of work required, and realized that the strategic question had already been answered, not in the Pacific, not in the skies over Midway or Coral Sea, but in steel mills and assembly lines thousands of miles away. The war was no longer just a test of courage or skill. It was a test of infrastructure, of industrial arithmetic in that arena. Japan was already behind. Essex was larger than Taiho. She displaced 27,100 tons standard compared to Taiho's 29,300 tons. And she carried 90 aircraft compared to Taiho's 75. And she was completed in 20 months, 12 months faster than Japan's fastest carrier construction program. That was not just faster, it was revolutionary. But that was only the beginning. Essex was the first of many. In January 1943 came Lexington, then Yorktown, then Bunker Hill, Intrepid Hornet, Franklin. By the end of 1943, the U.S. had commissioned 11 Essex-class carriers, 11 in just 1 year. Japan, by contrast, had produced a single new fleet carrier, Taiho 1. The Japanese naval staff pored over intelligence reports, trying to reconcile the numbers. They assumed propaganda must be exaggerating. Yet aerial reconnaissance intercepted communications, and photographic evidence all told the same story. The Americans were building carriers faster than Japan could replace losses, faster than Japan could train pilots to fly from them, faster than Japan could adapt its tactics to counter them. The secret lay with a man named Henry Kaiser. Kaiser had never built a warship before 1941. He was a construction engineer and industrial visionary. What he lacked in naval experience, he made up for with ingenuity, organization, and a single-minded understanding of mass production. Where Japan built carriers like artisan creations, Kaiser applied prefabrication, modular construction, and assembly line techniques to warships. Sections of hulls, flight decks, superstructures were built simultaneously in factories, then brought together and welded into a finished ship. The result was speed, scale, and efficiency Japan could not touch. By the time Taiho finally entered service in March 1944, the Americans were already commissioning multiple Essex-class carriers every few months. The numerical advantage Japan had counted on their years of experience. Their veteran pilots, their perfected tactics was being erased not in battle, but in shipyards. And with each new carrier launched, each air group trained, the industrial tide turned inexorably against Japan, setting the stage for a conflict they could no longer control. Kaiser's genius was not in naval tactics or carrier design. It was in organization, process, and sheer industrial ingenuity. He applied principles of mass production prefabrication, modular construction, and assembly line techniques to warship building. Hull sections, flight decks, and superstructures were built simultaneously in factories and brought together and welded into a finished ship. Where Japan built each carrier almost like a bespoke creation, Kaiser's shipyards churned them out with astonishing speed and consistency. By 1943, his methods were producing carriers faster than Japan could conceive. Every month, a new Essex-class ship slid into the water, fully equipped, fully armed, and ready to train its air group. Japan's single carrier, Taiho, could not compete. The numerical advantage that Japan had relied on the experience of its pilots, the perfected tactics honed over years. The supposed invincibility of its carriers was being erased by steel, welding torches, and the relentless efficiency of American industry. The naval staff in Tokyo could not ignore it. Every report, every photograph, Every intercepted message confirmed the same terrifying truth. The Americans were building carriers faster than Japan could replace them. Faster than they could train pilots. Faster than Japan could hope to respond tactically. It was not just a matter of skill or courage. It was arithmetic, production, and momentum. And in that industrial war, Japan was already losing Ozawa Yamamoto, and their colleagues could fight with brilliance, with audacity, with every ounce of courage and skill they had. But the Americans were counting, calculating, and building at a scale Japan could not match. The result was inevitable. No plan, no tactical maneuver. No desperate gamble could overcome the tide of steel that Kaiser was unleashing. Kaiser treated shipbuilding like he had treated dams. Roads and bridges like managing massive structures and massive workforces, not just crafting individual vessels. He divided each ship into prefabricated sections, built simultaneously in multiple locations, then brought them together to be welded into a finished whole. What had once taken 6 months could now be done in weeks. Workers were trained on the job, learning to weld instead of rivet. Tens of thousands of men and women, many seeing a ship for the first time, moved steel plates, engines, and superstructures with astonishing precision. By the end of 1941, the Richmond yards were humming. Each day, workers pushed the boundaries of what the skeptics called impossible. Ships emerged from the slipways in record time, rivets replaced by welds, and holes tested under the scrutiny of engineers who understood both structure and process. Where traditional shipbuilding saw risk, Kaiser saw opportunity. The risk of cracked welds was outweighed by the speed of production. One ship became two, two became 10, 10 became dozens. By 1942, Richmond yards were launching Liberty ships at a pace the world had never seen. A vessel that would normally take half a year could now be built in just weeks. The techniques developed in cargo ship construction would soon be adapted to warships, including aircraft carriers. Essex-class carriers, though massive and complex, could now be produced with the same philosophy: prefabrication, modular construction, and relentless organization. Japan's naval planners could not comprehend it. They had counted on their industrial advantage in Asia, on skilled shipwrights and meticulous construction, on carriers built like works of art. They had not anticipated men like Kaiser turning shipyards into machines, outproducing and outpacing them at every turn. The arithmetic of war, the numbers of carriers, aircraft, trained pilots, was shifting against Japan. Long before a single plane had taken off from Taihaho, Kaiser's success with Liberty ships gave him confidence and the Navy a reason to take a chance. Escort carriers were smaller and less complex than fleet carriers, but they still required flight decks, hangars, elevators, arresting gear, and the ability to handle aircraft safely at sea. Traditional shipbuilders insisted it would take years, that the risks of welding failures and inexperienced labor were too high. Kaiser saw it differently, using the same modular, prefabricated approach. The Vancouver yard broke the escort carrier into sections that could be built simultaneously. Workers, many of them women and African Americans, who had never been in a shipyard before, focused on mastering one module at a time. Engine rooms, flight decks, and superstructures were built separately. Oriented, however, it was easiest to weld, then lifted into place by massive cranes and joined with precision. The results were staggering. Casablanca, the first of the new escort carriers, went from keel laying on November 3, 1942, to launch on April 5, 1943, and was commissioned on July 8, 1943, just 8 months from start to finish. A ship that would normally have taken years to complete was now ready for combat in a fraction of the time. The modular system, once considered suitable only for simple cargo vessels, had proved itself in warship construction. Kaiser's methods didn't just produce ships, they produced speed, reliability, and momentum. Every escort carrier completed allowed the Navy to project air power more widely, to protect convoys, and to train pilots more rapidly. It was a preview of what would come when the same principles were applied to fleet carriers, Essex-class carriers, that could be built faster in larger numbers, with crews trained to use them effectively. making Japan's painstakingly built carriers seem almost obsolete before they even reached the front lines. By applying the same prefabrication principles that had revolutionized cargo and escort carrier construction, the Americans were now producing fleet carriers at a pace Japan could scarcely comprehend. Newport News, along with other shipyards, chopped the construction process into modules that could be built simultaneously. Hull sections, hangar decks, flight decks, and island superstructures were fabricated in separate shops, then transported and welded together on the slipway. Where Japan had once built each carrier almost as a single bespoke creation, the U.S. now built them like massive modular machines. The effect on the Pacific War was immediate and staggering. Task forces that had once seemed impossibly large began to appear with regularity. Where Japan had 6 carriers in total, the Americans deployed squadrons with a dozen, 15, even 18 carriers at a time. Each new carrier brought more aircraft, more trained pilots, and more operational flexibility. The numerical and tactical advantage Japan had relied on veteran pilots, perfected doctrines. Superior ship design was being erased, not in a single battle, but day after day, month after month, in the shipyards of the United States. For the Japanese naval staff, the reports were almost incomprehensible. Every encounter with American task forces confirmed what intelligence had already hinted at. The Americans were producing carriers faster than Japan could sink them, faster than Japan could train pilots to fly from them, and faster than Japan could develop countermeasures. The arithmetic of war, the balance of ships, aircraft, and trained crews was shifting inexorably against them. And the source of that shift was not the bravery of pilots or the cunning of admirals, was prefabricated steel, welding torches, and the relentless organization of men like Henry Kaiser. The numbers were staggering. Welding, standardization, and modular construction didn't just speed production, they multiplied it. Every worker became a specialist on one module, one component, one section of a ship, then repeated that work dozens of times. Shipyards became assembly lines, churning out vessels at a pace Japan could scarcely imagine. Franklin laid down on December 7, 1942, launched on October 14, 1943, and commissioned on January 31, 1944. Took just 13 months from keel to commissioning. Other Essex-class carriers were completed in 14 to 16 months, with the average around 18 months. By contrast, Taihoa, Japan's fastest carrier, had taken 32 months. In both speed and output, American shipyards were operating at twice the efficiency of their Japanese counterparts and producing far more ships in absolute terms. By March 1944, when Taiho finally joined the fleet, the United States had 17 Essex-class carriers in service or under construction, 17-1. That ratio didn't even account for the dozens of light carriers and escort carriers being launched simultaneously. The Americans were not just replacing losses, they were surging past Japan's entire naval capability, creating a force that could overwhelm Japan at every turn. Japanese planners had fought to preserve tactical brilliance, to extract every ounce of value from each carrier, to maximize skill, courage, and doctrine. But no level of ingenuity could overcome industrial arithmetic. Every new Essex, every escort carrier, every pilot trained, tilted the balance further. By 1944, the war was no longer just about tactics in the Pacific, it was about production, momentum, and the relentless ability to translate steel and welding torches into operational superiority. Japan's attempts to accelerate carrier production were heroic, but futile. The Unru-class carriers, Magi Katsuragi, and Unru were commissioned within 10 weeks, a remarkable achievement given the constraints. On paper, it looked like Japan was catching up. In reality, the Americans were surging ahead. During the same 10-week period, 9 Essex-class carriers joined the U.S. fleet. For every carrier Japan added, the United States added 3. The disparity wasn't just about shipyards or labor, it was about resources. Steel, the backbone of naval construction, was America's secret weapon. An Essex-class carrier required roughly 27,000 tons of steel. In 1944 alone, the United States produced 80 million tons of steel. Japan, by contrast, produced only 6 million tons, 10 to 1. That gap dictated every decision in Tokyo. Every plate, every beam, every ton of armor was precious. Mistakes could not be discarded. They had to be painstakingly repaired. Slowing construction and limiting scale, American shipyards operated with freedom, speed, and redundancy. If a section was flawed, it was scrapped and replaced. Hulls could be prefabricated in sections, welded together rapidly, and outfitted with machinery and armor without hesitation. The U.S. could absorb losses, mistakes, and modifications without slowing the overall program. Japan had no such luxury. Each delay compounded the problem. Workers repaired damaged steel, adjusted designs, and stretched limited resources over multiple projects simultaneously. Even the untold class, Japan's mass production solution, could not match the pace or output of a single American shipyard. The consequences were clear to those who understood the arithmetic. Japan's carriers might still fight brilliantly in battle, but the United States could outproduce, outreplace, and outlast them. Every time Japan pushed harder, America pushed faster. Every attempt to close the gap only widened it. The industrial tide that Kaiser and American shipbuilders had unleashed was now unstoppable, and Japan's carriers were being swallowed in the current. The difference in scale and organization was staggering. American shipyards were modern industrial machines. Thousands of powered lathes, drill presses, milling machines, and welding stations allowed precision work at high speed. When a machine broke down, spare parts were on hand, and production continued. Japanese yards, by contrast, struggled with old, worn-out equipment, limited replacements, frequent breakdowns that halted construction for days or weeks. Workforce was another decisive factor. By 1943, American shipyards employed 2 million workers. Kaiser's Richmond yards alone had 90,000 people, more than all three of Japan's major naval shipyards combined. Most were inexperienced. Women who had never held industrial jobs, teachers, office clerks, farm wives. Yet within weeks, they were welding, riveting, operating cranes, and reading blueprints. Traditionalists scoffed. They insisted only trained, experienced shipwrights could produce quality vessels. But Kaiser's system didn't require years of apprenticeship. It required repetition, precision, and standardization. Each worker mastered a single task and repeated it hundreds of times. A welder didn't need to understand the structure of the ship or the mechanics of the engine room. She needed to know exactly how to weld a specific seam at a specific angle, using the jigs and fixtures provided. The same blueprint guided every station. One worker built one module. Another built another. Modules were later lifted, aligned, and welded together. The ships practically assembled themselves from prefabricated pieces, while the workforce, diverse, largely untrained, and rapidly educated, became the engine that drove an industrial tidal wave Japan could not match. In essence, American shipbuilding had become an assembly line on an unprecedented scale, faster, more precise, and more flexible than any naval planners had imagined. Japan could fight with the skill and courage of its sailors and pilots, but no level of heroism could overcome a workforce of millions. Standardized production methods, and a shipyard system designed to produce carriers faster than they could be sunk, repetition created expertise. After a month, workers became fast. After 2 months, they became precise. After 3 months, they could work faster than traditional shipwrights who had spent years mastering their craft. In contrast, Japanese yards could not replicate this model. Japan employed roughly 300,000 shipyard workers, many skilled craftsmen, but they were spread thin across dozens of projects. Training new workers was slow because experienced artisans were already occupied with demanding tasks. The difference ran deeper than numbers. It was cultural and philosophical. Japanese shipbuilding prized craftsmanship. A skilled shipfitter took pride in custom fitting each piece, adjusting plates, beams, and joints to ensure perfect alignment. The result was beautiful, precise ships, but The process was slow and labor-intensive. American shipyards, by contrast, standardized everything. Parts were manufactured to exact specifications in prefabrication shops. They either fit or they were discarded. Waste was acceptable because speed and scale mattered more than perfection. The disparity extended to workforce organization. Americans could specialize. One crew fabricated bulkheads, another built deck sections, another installed propulsion machinery. Specialization multiplied output and accelerated production. Japanese yards relied on generalists, workers trained to fit holes, install machinery, and handle electrical systems. Flexibility was high, but speed suffered. Newport News Shipbuilding, which produced the bulk of Essex-class carriers, epitomized this industrial philosophy. Entire assembly areas were dedicated to single tasks. One 500-foot building fabricated only flight deck sections. Each module was built simultaneously, then moved into position on the slipway for final assembly. By compartmentalizing tasks, standardizing methods, and leveraging repetition, American yards produced carriers faster, in greater numbers. And with trained crews ready to deploy a combination Japan's industrial culture, resources, and workforce could never match. The contrast between the two nations approaches the Japanese pursuit of perfection versus the American drive for speed would define the course of the Pacific War. Craftsmanship could win individual battles, but in a war of industrial scale, speed and scale determined who survived and who was swept aside. When the modules were ready, they were transported by crane to the shipway and lifted directly into position in the hull. Connections to steam lines, electrical systems, and instrumentation were completed in days rather than months. Testing had already been performed in the shop, so the risk of failure during installation was minimal. Where traditional shipbuilding relied on painstaking assembly, piece by piece inside cramped holes, Newport News had transformed the process into a controlled, predictable, and rapid workflow. Flight deck sections, elevators, and propulsion modules were just part of the story. Hangar decks, bulkheads, and superstructures were fabricated the same way, prefabricated in specialized shops, lined in assembly jigs, and welded together in modular sections. Entire carrier hulls were gradually built up from these pre-tested modules. A section that might have taken 6 weeks, using traditional methods, could now be completed in a fraction of that time, 8 days for a flight deck section. With consistent quality and precision, this approach extended to every complex subsystem. Hydraulic systems, ventilation, electrical cabling, and weapons foundations were pre-assembled wherever possible. Cranes moved modules from shop to ship. Teams of workers completed their specialized tasks in a sequence dictated by workflow optimization rather than tradition. By breaking carriers into hundreds of repeatable, manageable components, the yard turned a complex, years-long construction process into a production line measured in months. The results were profound. Essex-class carriers, which once would have required years of construction, could now be completed in 18 months on average. Key subsystems were tested and verified before ever reaching the hull, minimizing downtime. Repetition, specialization, and modularization produced not just speed, but reliability. Ship emerging from the yard ready to integrate aircraft, train crews, and join the fleet far faster than Japan could match. Every subsystem followed the same philosophy. Radar, communications, crew accommodations, even ventilation ducts and ladders, all were standardized, prefabricated, and tested before installation. Nothing was custom fit. Workers moved from one pre-assembled component to the next, installing and connecting them with speed and precision. Errors were minimized because each piece had been verified in the shop before it reached the hull. This modular, pre-tested approach compressed construction timelines dramatically. Flight decks, elevators, propulsion modules, and superstructures were already complete before being lifted into place. Systems were connected and verified in weeks rather than months. Crew spaces arrived fully outfitted, ready for habitation as soon as the ship was afloat. The result? Essex-class carriers could move from keel laying to launch in 6 to 8 months. then spend another 6 to 8 months in outfitting, testing, and trials. Total time from start to operational ship, 14 to 16 months. In contrast, Japanese carriers like Taiho required more than twice that time. Every plate, every system, every component was handled individually, often by small teams of highly skilled workers who lacked the industrial redundancy and specialization of American yards. Errors had to be repaired on the spot, delays compounded, and material shortages further slowed production. The Japanese approach produced craftsmanship, but it could not compete with the speed, scale, and repeatability of modular construction. By 1944, the industrial consequences were clear. The U.S. Navy could deploy carrier after carrier, task force after task force, while Japan struggled to bring a handful of ships into service. Every innovation in prefabrication, standardization, and modular workflow translated directly into operational advantage. Turning steel, welding torches, and machine tools into a force Japan could not match no matter the skill of its pilots or the bravery of its sailors. Japan couldn't match American production for 3 critical reasons. First, they lacked the industrial infrastructure for true mass production. Prefabrication required factories capable of producing thousands of identical components to precise tolerances. American industry had decades of experience from automobile, appliance, and consumer goods manufacturing. Factories were built around assembly lines, standardized parts, and interchangeable components. Japanese industry, by contrast, was largely small-scale and custom-oriented. Precision parts came from specialized machine shops rather than high-volume assembly lines. To replicate American methods, Japan would have needed to build entirely new factories, train new workforces, and create entirely new supply chains. They had neither the time nor the resources to make such a transformation. Second, Japan lacked the raw material capacity to support prefabrication at scale. Prefabrication is inherently wasteful. Steel is cut in excess. Components that fail tolerances are scrapped, and inventory buffers ensure production never stops. When Kaiser's Richmond yards built a Liberty ship, they ordered roughly 15% more steel than the ship actually required. That surplus absorbed waste, mistakes, and rejected parts while keeping the workflow continuous. Japan, with limited steel production, could not afford such redundancy. Every plate, beam, and structural element had to be used. Errors had to be repaired in place rather than discarded. The result was slower, more labor-intensive construction with no room for accelerated production. The third disadvantage, which compounded the first two, was labor. American shipyards could rapidly train unskilled workers to perform one specialized task repeatedly. Japanese shipyards relied on skilled craftsmen who were already overextended across multiple projects. Training new workers was slow and industrial. Culture emphasized craftsmanship over standardization. While the Americans built carriers and modules, pre-tested systems, and repetitive tasks, Japanese workers were required to fit, assemble, and test components on site, often improvising solutions in cramped spaces. Precision and pride came at the cost of speed and scalability. These 3 factors, industrial infrastructure, raw material capacity, and workforce organization, meant that no matter how much Japan accelerated its carrier programs or innovated in design, it could never match the output of American shipyards. The gap was not a temporary setback. It was a structural disadvantage baked into the war from the start. American prefabrication worked because raw materials and components could flow reliably from factories to shipyards. Steel from Pennsylvania, turbines from Ohio, electronics from California could be shipped by rail to Newport News, Norfolk, or Richmond in days. If one supplier faltered, another could fill the gap. Redundancy and abundance made the system resilient. Japan had no such luxury. Its transportation infrastructure was limited, and heavy components often traveled by coastal shipping rather than rail. A turbine built in Kobe might take 2 weeks to reach Yokosuka. And if the ship carrying it was sunk, which happened regularly, the entire unit was lost and a replacement had to be produced. Shipyards slowed, construction schedules stretched, and precious steel and labor were wasted. Supply chain vulnerabilities became more crippling than any single design flaw or labor shortage. The logistics gap extended to every aspect of production. American yards had reliable access to steel, aluminum, copper, rubber, and electronics. With multiple suppliers and transport routes, Japanese yards depended on steel from Korea and Manchuria, copper from the Philippines, and rubber from the Dutch East Indies, materials that had to traverse seas increasingly dominated by American submarines. By 1944, Japan was losing merchant shipping faster than it could replace it. Even if a shipyard could work at full efficiency, it lacked the raw materials to sustain output. The combined effect of scarce steel, slow and vulnerable transportation, and fragile supply chains made rapid Japanese carrier construction impossible. Japan could innovate, adapt designs, and train skilled crews, but industrial reality dictated the pace of production. Meanwhile, American shipyards, fueled by abundant materials, reliable transport, and modular production, continued to surge forward. Every month, every ship launched. Every trained air group added to the U.S. fleet increased the pressure on Japan, ensuring that no tactical brilliance could overcome the structural imbalance of industrial power. Critical materials weren't arriving on time. Shipyards stalled, waiting for steel plate, turbine blades, or electrical cable. Taiho had been designed with 8 boilers and 4 turbines, producing 160,000 shaft horsepower. But 2 of the Unru-class carriers, Katsuragi and Amagi, had to make do with destroyer engines because turbine manufacturers couldn't produce fleet carrier power plants fast enough. Their top speed dropped to 25 knots instead of the designed 34. Slower carriers meant less tactical flexibility. They couldn't evade attacks, close with enemy forces, or retreat when danger loomed. The Americans faced no such compromises. Every Essex-class carrier had identical propulsion systems, 150,000 shaft horsepower and a top speed of 33 knots. Standardization ensured predictability in planning, deployment, and battle operations. Japanese carriers, meanwhile, were slow, piecemeal, and operationally constrained by factors far beyond the skill of their crews. Carrier construction was only half the struggle. Training pilots to operate from those carriers was equally increasingly impossible. Before the war, Japan had the world's best naval aviators, trained for 2 years before their first carrier landing. They practiced navigation, gunnery, formation flying, night operations, and carrier approaches. By 1943, Japan had neither the time nor the resources to maintain such rigorous programs. Submarine attacks on merchant shipping meant fuel shortages, forcing training programs to shrink. Flight hours were cut from 500 to 100. Pilots could take off, fly, and shoot, but they lacked the experience to survive combat against veteran American aviators. Saburo Sakai, one of Japan's top aces, with 64 kills, was pulled from combat in early 1943 to serve as a flight instructor. He was shocked by what he found. Cadets struggled with basic carrier landings. Formation flying was sloppy. Navigation errors were common. The program was overwhelmed. Even Japan's elite instructors could not compensate for shortages of fuel, aircraft, and flight hours. Experienced pilots were burned out, reserves depleted, and replacements underprepared. Industrial constraints, logistical failures, and truncated training created a cascading effect. Japan could design carriers, plan operations, and fight tactically, but its ships and pilots were increasingly incapable of matching American numbers and proficiency. The stage was set when the fleets clashed. Even brilliant Japanese tactics could not overcome the grinding arithmetic of American production and training. Instructors were overwhelmed. Classes rushed, and fundamental skills skipped. Sakai later wrote that cadets were told to forget the fine points, just teach them how to fly and shoot. Graduates were brave and dedicated, willing to die for their country. But they weren't ready for combat. At the Battle of the Philippine Sea in June 1944, Japan sent 450 carrier aircraft against American task forces. American fighters shot down 300 of them in a single day. The engagement became known as the Great Marianas. Turkey Shoot, a brutal demonstration. Of the consequences of Japan's industrial and training deficiencies, Japan committed 9 carriers to the Battle 3 fleet. Carriers Taiho Shokaku, Zuikaku, and 6 light carriers Kitos, Chiyoda, Junyohyo, Ryu, and the newly commissioned Unru. Those 9 carriers carried 450 aircraft, less than half the capacity they were designed for. Japan simply lacked the planes to fully equip its ships. Worse, the pilots were undertrained. With only 6 months of flight instruction compared to the 2 years typical before the war, they could take off land and fly basic formations. But they lacked combat experience against veteran American aviators. American Task Force 58, commanded by Admiral Mark Mitcher, fielded 15 Carrier 7 Essex-class fleet carriers and 8 light carriers, embarking 956 aircraft. That was more than twice Japan's total, and the American aircraft were superior. The F-6F Hellcat had a maximum speed of 380 mph. Compared to the Zero's 340 miles per hour, the Hellcat could dive at 450 miles per hour without structural failure. The Zero's maximum dive speed was 360 miles per hour. The result was catastrophic. Japanese air groups were shot down in waves. Carrier-based aircraft lacked coordination, experience, and the margin for error to survive against a numerically and technologically superior foe. Japan's losses were not merely tactical, they were structural. The combination of inadequate pilot training, insufficient aircraft, and limited carrier numbers exposed the consequences of an industrial gap that no skill or courage could overcome. The Hellcat was a flying fortress compared to the fragile Zero. Pilot armor, self-sealing fuel tanks, and an armored engine cowling allowed it to absorb tremendous battle damage and continue flying. The Zero had none of these protections. A single burst of machine gun fire through the fuel tank could ignite it, and pilot casualties were nearly certain. The Hellcat mounted 6.50 caliber machine guns with a combined rate of fire of 1,800 rounds per minute. The Zero carried 2 20mm cannons and 2 7.7mm machine guns, respectable armament. But far less sustained firepower experience tipped the scales decisively. The average American pilot in Task Force 58 had 200 hours of combat flight time. Many had 300 or more. They had fought at Tarawa Truck, Hollandia, and dozens of smaller engagements. They understood their aircraft's limits, how to exploit the Hellcat's strengths, and how to outfight Zeros. The average Japanese pilot, by contrast, had only 20 hours of combat flight time. Some had none. They were flying their first carrier operation against the largest, most experienced naval aviation force in history. The outcome was catastrophic and immediate. At 7:30 a.m. on June 19th, Japan launched its first strike wave, 69 aircraft. American radar detected them 150 miles out. Fighter directors vectored 40 Hellcats to intercept. The American pilots engaged. The Japanese formation 40 miles from the carriers, shooting down 42 aircraft in the first 10 minutes. The survivors pressed on, only to encounter a second wave of Hellcats, a third wave, and concentrated anti-aircraft fire from screening cruisers and destroyers. Only 8 aircraft reached the carriers, scoring no hits. 4 managed to return. Japan's first strike lost 94% of its aircraft before it could inflict any meaningful damage. The second strike, launched at 8:56 a.m., fared no better. Of 109 aircraft, 97 were destroyed before reaching attack range. The third strike, 107 aircraft, achieved a single bomb hit on the battleship South Dakota, causing minor damage. Across all 3 waves, Japan's losses were staggering. Hundreds of aircraft destroyed in minutes, pilots killed or captured, and carrier air groups decimated. The Great Marianas Turkey Shoot exposed the full consequences of Japan's industrial, training, and logistical failures. Aircraft could be built, but not in sufficient numbers. Carriers could be constructed, but too slowly. Pilots could be trained, but never quickly enough to match American experience. Against a fleet operating with overwhelming numbers, superior. machines, and battle-hardened crews, tactical brilliance alone could not compensate. Japan's naval aviation was, in a single day, rendered almost irrelevant. The fourth strike disintegrated into chaos. Some aircraft found American carriers, but were driven off. Others never located the enemy and returned with bombs still attached. Of the 450 aircraft launched, 300 were shot down in combat. Another 50 crashed, attempting to land on their carriers in darkness after the battle. Japan lost 350 aircraft and their pilots in a single day. American losses totaled 29 aircraft. The exchange ratio, roughly 12-1 in America's favor, reflected not just superior planes, pilots, and doctrine, but the cumulative consequences of Japan's failed carrier construction and pilot training programs. If Japan had been able to match American production, they might have deployed 20 or 30 carriers to the Philippine Sea instead of 9. Even with inferior aircraft and undertrained pilots, sheer numbers over 1,000 aircraft could have complicated American defenses and potentially inflicted meaningful damage. But Japan had 9 carriers, and by the end of the battle, 3 were gone. Taiho Commission, just 3 months prior, was hit by a single torpedo from the submarine Kavala. Japanese damage control doctrine was sound for torpedo hits, but a critical error by a young officer proved fatal. System turned on to clear gasoline fumes from the hangar deck, inadvertently spreading the vapor throughout the ship. 6 hours after the torpedo strike, a spark ignited the fumes. The explosion tore Taiho apart. She sank in minutes, taking 1,272 men with her. 32 months of construction, 3 months in service, gone. Shokaku, a veteran of Pearl Harbor. Coral Sea, in Santa Cruz, was hit by 4 torpedoes from the same submarine. She sank 7 hours later. Hio, struck by aerial torpedoes and bombs, caught fire, lost power, and also sank. In a single day, Japan lost 3 carriers, most of its experienced air crews, and its ability to project power in the Central Pacific. The Philippine Sea demonstrated the strategic consequences of Japan's industrial imbalance. Carriers that took years to build, trained pilots that required months to reach competency, and painstakingly assembled air groups were no match for American industrial scale, modular construction, rapid pilot training, and overwhelming numbers. Even tactical brilliance could not compensate for the crushing arithmetic of production, logistics, and training. The battle left Japan's carrier force crippled, its remaining ships vulnerable, and its operational options sharply limited. By late 1944, Japan's carrier force was effectively finished. At the Battle of Leyte Gulf in October, the Japanese committed their remaining carriers as a decoy force. For carriers, nearly empty of aircraft, sailed north to draw American forces away from the main battle area. The plan worked tactically. American carrier aircraft attacked the decoy, sank all 4 ships, but strategically, it achieved nothing. American escort carriers engaged and neutralized the Japanese surface fleet regardless. The decoy cost Japan its last carriers with no strategic gain. Zuikaku, the last of the 6 carriers that had attacked Pearl Harbor, went down on October 25, 1944. She had survived 3 years of combat, only to be sunk because Japan lacked enough aircraft or trained pilots to defend her. By November, Japan had no operational fleet carriers remaining. America had 28. The advantage was not merely numerical, it was systemic. When an Essex-class carrier was damaged, it could sail to a naval yard for repairs. Repairs were completed in weeks or months thanks to prefabricated replacement sections, standardized parts, and massive repair facilities. USS Franklin, operating off the Japanese coast, was hit by 2 bombs on March 19, 1945. The bombs penetrated the flight deck and exploded in the hangar, igniting secondary explosions from fueled and armed aircraft. Fires raged for hours, and 87 men were killed. The ship was dead in the water, listing and threatening to explode. Any other navy might have abandoned her, but American damage control teams fought methodically. Fires were contained, the list stabilized, and engines restarted. Franklin sailed to Pearl Harbor under her own power at 14 knots, then transited to the Brooklyn Navy Yard for further repairs. Arriving on April 28, 1945, a ship that should have been lost had been restored. Through industrial depth, standardized design, and highly trained support, crews a stark contrast to Japan, whose losses were irreversible. The difference was not luck. It was the result of decades of industrial development. The systematic application of prefabrication, modular construction, logistics planning, and workforce training. Japan had built brilliant carriers and trained elite pilots, but they were finite resources. America had built a machine that could replace losses faster than Japan could inflict them, and by 1944, that machine had destroyed the core of Japanese naval aviation. The war ended before USS Franklin could return to full service. She survived. That level of damage control was impossible for Japan. Japanese carriers hit by major attacks usually sank or had to be scuttled. Japan lacked the repair facilities, the replacement parts, and trained damage control teams necessary to save heavily damaged ships. The difference in industrial capacity manifested in every aspect of carrier operations. American carriers were equipped with radar. Type SK air search radar could detect incoming aircraft at 90 miles, while Type SM height finding radar determined altitude. Fighter directors used this information to vector interceptors onto incoming strikes long before they reached the fleet. Japanese carriers had limited radar. Early models could detect aircraft only at 30 miles under ideal conditions. And night operations or bad weather drastically degraded performance. Japanese fighter directors relied on visual sightings and radio reports from picket ships. American carriers also employed proximity fuse anti-aircraft shells. The VT fuse used a miniature radar to detect nearby aircraft and detonate automatically, increasing effectiveness by 5 to 10 times compared to contact or timed fuses. Japanese carriers, in contrast, used traditional contact or timed fuses, which required a direct hit or precise timing to achieve destruction, far less effective in combat. Aircraft quality further widened the gap. American planes were faster, more durable, better armed and armored. Fighters like the F-6F Hellcat could absorb damage and keep flying. Bombers could survive hits that would destroy their Japanese counterparts. Japanese aircraft, optimized for maneuverability and range, lacked armor, self-sealing fuel tanks, and redundancy. Even highly skilled pilots were vulnerable to attrition once. American numbers and technology overwhelmed them. By the final year of the war, these advantages radar, fire control, proximity fuses, standardized high-quality aircraft, and repair capacity meant that American carriers could operate continuously, recover from damage, project overwhelming air power, and sustain losses without strategic disruption. Japan, in contrast, was running on the edge of exhaustion. One strike could destroy a carrier, one torpedo could wipe out a ship for good, and losses of aircraft and trained pilots could not be replaced. The industrial and technological gap had become decisive. The F-6F Hellcat could outperform the A-6M0 in nearly every category. Higher speed, superior climb rate, faster diving speed, heavier armor, and more potent armament. Japanese carriers were still reliant on the Zero, largely unchanged since 1941, while the Zero was lighter and more maneuverable. It was slower, more fragile, and incapable of destroying armored American aircraft quickly. American carriers also benefited from superior doctrine. Fighter sweeps cleared the skies before strikes. Combat air patrols protected the fleet from incoming attacks. Radar-directed intercepts ensured fighters engaged enemies well before they reached the fleet. Japanese doctrine, in contrast, emphasized the all-out assault. Launch every plane at maximum force, hit the enemy, and hope to sink carriers before they could respond. This worked at Pearl Harbor under conditions of surprise. It failed at Midway, where American carriers were prepared, and catastrophically at the Philippine Sea, where radar-directed American fighters slaughtered incoming waves by 1945. The Japanese Navy had effectively ceased to exist as a fighting force. Battleships, cruisers, and destroyers remained. But without carrier-based air cover, they could not operate in regions within range of American carrier aircraft. The few surviving Japanese carriers were relegated to training or transport roles because Japan lacked the pilots, planes, and industrial capacity to operate them effectively. Meanwhile, the United States Navy possessed more carrier air power than every other navy combined. Task Force 38, operating off Japan in July 1945, included 17 fleet carriers and 6 light carriers. Each carrier carried hundreds of aircraft, all trained, experienced, and equipped with the latest technology. The fleet could strike anywhere in the Japanese home islands with impunity, sustain continuous operations, replace losses faster than Japan could respond. By this point, the outcome of the carrier war, and by extension, the Pacific War, was no longer determined by tactics, bravery, or individual battles. It was determined by the arithmetic of industrial capacity, training pipelines, standardized design, and logistics. The carriers, planes, and pilots Japan had invested decades to build were outnumbered, outproduced, and outmatched by American systems engineered for continuous, overwhelming output. By the war's end on August 15, 1945, the imbalance was absolute. Japanese carrier production had yielded 6 ships, 3 Untold-class fleet carriers, and 3 converted light carriers. America had commissioned 20 carriers during the same period: 4 Essex-class fleet carriers, 9 Independence-class light carriers, and over 100 escort carriers. The final ratio was roughly 20-1. For every Japanese carrier built during the war, America had produced 20. That ratio alone encapsulated the decisive factor in the Pacific War: industrial capacity. Japan had entered the war with the finest carrier force in the world, built over 2 decades by highly skilled naval architects and shipbuilders. America began with an untested carrier fleet constructed in shipyards that were learning on the fly. Yet the United States had what Japan could never match: abundant industrial infrastructure. Raw materials, technological innovation, and the ability to learn, adapt, and scale production exponentially. The lessons of the carrier war were clear. Industrial capacity matters more than tactical brilliance. Japan possessed superior doctrine, highly trained pilots, and advanced aircraft in 1941, for 6 months. Those advantages allowed them to dominate every engagement. But tactical advantages erode over time. Pilots are killed, aircraft become obsolete, and doctrine must evolve. Industrial advantages, in contrast, compound. Every new carrier built by America made it easier to build the next. Every trained worker accelerated the training of the next cohort. Every factory optimized for mass production multiplied output by mid-1944. Tactical skill alone could not compensate for the arithmetic of production. Japan's carriers, pilots, and planes, once the pinnacle of naval aviation, were outnumbered, outpaced, and outproduced. The Philippine Sea, Leyte Gulf, and the final strikes against the Japanese homeland were not just victories of strategy or valor, they were victories of industrial design, modular construction, logistics, and scale. The carrier war had become a race that could not be won on skill alone. It was a race against steel, labor, and the relentless arithmetic of American industry. Asterisk, by the time the guns fell silent, the United States Navy's carrier force had become an instrument of overwhelming power, and Japan's once feared naval aviation had become a testament to the limits of tactical brilliance. When unmatched by industrial might, every standardized component made the American supply chain more efficient. By mid-1943, U.S. carrier construction had become a self-reinforcing system. Shipyards were completing carriers faster than crews could be trained to operate them. Japan never achieved that momentum. Every carrier they built consumed scarce resources needed for the next one. Every worker trained pulled manpower from production. Every attempt at standardization required retooling factories already stretched to the limit. The gap widened not incrementally, but exponentially. The numbers tell the story. In early 1942, Japan had 8 operational carriers. America had 3. By mid-1943, Japan had 6. America had 14. By mid-1944, Japan had 7. And America had 32. By early 1945, Japan had 0. America had 39. This progression wasn't linear. It was geometric. American carrier strength doubled, then tripled, then quadrupled. While Japanese strength steadily declined, the pattern repeated across every category of naval construction. Japan built 6 fleet carriers during the entire war. America built 24 Essex-class fleet carriers. Japan built 3 light carriers. America built 9 Independence-class light carriers. Japan completed no escort carriers. America completed 77 Casablanca-class escort carriers, plus dozens of other types. Total carrier production tells the full story. Japan produced 9 carriers in 3.5 years of war. America produced 110 in the same period, a ratio of roughly 12-1. And even that ratio understates the actual disparity. American carriers were larger, carried more aircraft, had superior radar, more effective anti-aircraft defenses, better damage control, and superior logistical and operational support. By 1944, the arithmetic of industrial capacity had rendered Japanese tactical brilliance irrelevant. The Pacific War had become a contest of production, training, and systemic efficiency, and in that contest, Japan had no hope. Every new American carrier compounded the advantage, ensuring that victory was no longer a question of strategy or courage. It was inevitable. An Essex-class carrier could operate 90 aircraft. A untold-class carrier could operate 65. An Essex-class carrier could make 33 knots. Some Japanese carriers, equipped with emergency destroyer engines, could barely make 25 knots. An Essex-class carrier had comprehensive radar coverage. Japanese carriers had limited radar that often failed at critical moments. That 12-1 numerical advantage in carriers translated into roughly a 20-1 advantage in actual combat capability. American carriers' worth of combat power for every Japanese carriers. By mid-1944, that level of superiority made naval combat in the Pacific effectively one-sided. Japanese surface forces could not operate within range of American carriers without being destroyed. Japanese bases could not function without being neutralized. Japanese supply lines could not operate without being severed. The Pacific War became a relentless campaign of American carrier aviation striking. Japan, while Japanese forces watched helplessly from shrinking defensive perimeters, by July 1945, American carrier task forces operated off the Japanese coast with impunity, launching thousands of aircraft strikes against cities, factories, ports, and military installations. Japanese air defenses were hopelessly outnumbered, often facing 50 American aircraft for every 1 Japanese fighter. The war did not end because of atomic bombs, though those provided a convenient pretext for surrender. It ended because Japan had no military capacity left to resist. Carrier aviation had destroyed that capacity, and carrier production had created the aviation that won the war. Henry Kaiser, the dam builder, who had never constructed a ship before 1941, revolutionized shipbuilding by applying mass production techniques, prefabrication, and modular construction. His work, combined with American industrial infrastructure, training systems, and logistics, created an unstoppable force. The outcome of the Pacific War was determined not by courage, doctrine, or tactical brilliance, but by the arithmetic of steel, labor, and standardized components. In the end, Japan's decade-long investment in superior carriers, pilots, and doctrine was rendered meaningless by the exponential power of American industry, a power that could not be fought on the battlefield, only measured in tons of steel, hours of training, and the relentless output of shipyards. Industrial capacity, above all, had decided the Pacific War. America built 110 in the same period. 6 to 110, every other comparison from aircraft, pilots, radar systems, anti-aircraft weapons. To repair capacitor, enforce the same truth. The Pacific War was lost long before the first bombs fell on Midway or the Philippine Sea. Japan had entered the conflict with the finest carrier force in the world. But America entered with something Japan could never match: industrial power multiplied by innovation, standardization, and scale. Newport News shipbuilders learned from Kaiser. Richmond shipyard workers, many of them women who had never held a wrench before. 1942 built carriers in months that should have taken years. America's modular mass production approach created a self-reinforcing cycle. Faster construction enabled faster training, faster deployment, and faster replacement. Every assumption the Japanese made about American capacity was wrong. Admiral Yamamoto had predicted 6 months to a year of Japanese dominance. Even that underestimated the speed and scale of American mobilization. He thought it would take 2 years for America to replace carrier losses. It took 9 months. He expected peak American carrier production at 8 to 10 per year. America produced 18 in 1943 alone. He assumed American pilots would take years to match Japanese skill. By early 1943, they were outfighting Japanese aviators in combat. By the end, the arithmetic was undeniable. Japan, 6 carriers. America, 110. Japan's finest pilots and ships were overwhelmed, not by luck or courage, but by an industrial system capable of producing carriers, aircraft, and trained personnel at scales Japan could never achieve. The war had been lost the moment it began, not on the decks of battleships or in the skies over Midway, but in factories, shipyards, and assembly lines across the United States. Industrial capacity, more than anything else, determined the outcome of the Pacific War. The exact number varies depending on how conversions and reclassifications are counted, but 6 is the commonly accepted figure for purpose-built Japanese fleet carriers completed during the war. America built 17 Essex-class fleet carriers during the war years. Add the 9 Independence-class light carriers, and the total rises to 26. Include the 77 Casablanca-class escort carriers, and it jumps to 103. With other escort carrier classes included, the total exceeds 130 carriers commissioned during the war. The title stopped counting isn't literally true. The Navy counted every ship, but the numbers became so large that individual carriers ceased to matter strategically. By late 1944, losing a carrier in combat was tactically unfortunate, but strategically irrelevant. Another carrier would arrive next month. For Japan, however, losing a single carrier was a national crisis. Prayers were said, memorial services held, recriminations launched against commanders who failed to protect irreplaceable assets. The emotional and strategic response to carrier losses tells everything about the industrial gap between the two nations. For Japan, every carrier was precious. Losing one meant months or years to replace it. For America, every carrier was important. Losing one meant waiting weeks for the replacement already under construction. That difference in industrial capacity was more decisive than any battle, any admiral's brilliance, or any tactical innovation. Industrial capacity won the Pacific War. Not courage, not sacrifice, not tactical brilliance. Not warrior spirit, but steel, welding torches, and assembly lines. That lesson remains as relevant today as it was in 1945 for anyone studying warfare, strategy, or international competition. It wasn't small, it was a chasm. By mid-1945, the United States was building, or had planned more carriers than Japan could ever hope to field in a lifetime of war. Every new American carrier meant more aircraft, more trained pilots, more operational experience. Every Japanese carrier consumed scarce steel, burned through precious man-ores, and yet never came close to replenishing losses. The arithmetic was brutal and inevitable. Japan could fight battles, but it could not fight the war. Understanding this was the cruel clarity Vice Admiral Ozawa faced on Taiho's bridge. The enemy was not just across the horizon, it was in the factories, the assembly lines, the standardized components flowing seamlessly from coast to coast. By the time Japan lost a single carrier, America had replacements already under construction, some to be launched weeks later, others already completed. Industrial capacity had become a weapon far more lethal than any torpedo or bomb. The Pacific War had been decided long before the first carrier planes took off over Midway. The Coral Sea or the Marianas? It was decided in the shipyards of Richmond, Newport News, and across America through welding torches, assembly jigs, prefabricated modules, and an unrelenting, self-reinforcing system that Japan could neither match nor escape. By the time Japan realized the scale of the problem, the die was cast. Industrial power, more than courage, more than doctrine, more than the warrior spirit, had already determined the outcome. The rest was merely cleanup. The contrast is staggering. In the same 3 years, the Americans built 17 Essex-class fleet carriers, plus over 100 escort carriers, and countless support and merchant vessels. The sheer scale of production created a self-reinforcing advantage. Every ship launched meant more pilots trained, more crews experienced, and more industrial processes refined. Japan's finest carriers, built over decades with the most skilled workers, could not compete with a system that treated shipbuilding as a continuous, scalable machine. The Pacific War was less a contest of tactics or courage by mid-1943-44, and more a demonstration of industrial mathematics. Numbers didn't just add up, they multiplied. Every Japanese carrier lost was a catastrophic blow. Every American carrier launched barely registered on a strategic scale. By the time Japan realized the magnitude of the disparity, the outcome was inevitable. The factories had already decided the war, the story of the Pacific. War isn't just about battles, it's about factories, assembly lines, and the power of industrial capacity to decide the fate of nations. Every weld, every prefabricated module, every new worker trained contributed to a force Japan could never match. The ships may have sailed into combat, but the war was already won long before they left the shipyard. By sharing these stories, we remember not only the heroism on the battlefield, but also the unseen struggle in shipyards and factories that shaped the course of history. Your support helps keep these lessons alive for future generations. Thank you for watching, for learning, and for honoring the past.